The next recorded talk will be from David Scaramuzza, who's a professor of robotics and perception at the University of Zurich. He did his PhD at ETH Zurich and a postdoc at UPenn. And his focus really is on, robotics, computer vision, machine learning, and then really using standard and event-based cameras to do autonomous, agile micro drones for search and rescue applications. So from all the robots we've seen so far, which are relatively slow, to something that is super fast and dynamic, he has a number of awards, and I'm just going to mention the ERC awards, the IEEE Robotics Association Society Early Career Award, European Young Research Award, and a slew of others. So let's see if we can get this video playing.
So I want to tell you the journey that I've been working on in my lab for the past 10 years on autonomous navigation of drones, only relying on onboard cameras. More recently, meaning in the past few years, we actually moved on and trying to enable drones to move very agilely. So that means at very high speeds with very high angular accelerations. Next slide. So what we are actually currently focusing on is on trying to make autonomous drones fly as good or even better than human pilots are today. What you see in this video is some of the many thousands of videos that are uploaded on YouTube every day, where first-person view drone racing pilots actually outweigh their own performance, trying to pass through a series of obstacles in the fastest possible time. So human drone racing pilots are impressive because they have to cope with the motion blur, with the large latencies due to their brain, by the way, behavioral latencies, plus the latencies of the video transmission system in order to fly these drones super agile. And flying drones super agile is actually very important in applications like delivery, search and rescue, and any application where actually you want to get from A to B in the fastest possible time. And this is actually very important nowadays because, drones have a very limited battery capacity. So if you can increase the distance covered by the drone, they will be able to accomplish more in their limited battery time. Next slide. So how do humans navigate drones? Well, humans actually navigate drones only vision-based. So that's why actually we rely on vision-based drones in my lab. And what you see in this slide is our most recent autonomous drone. So this drone that you see here, it's about this size, about 18 centimeters in size. It weighs less than 1 kilogram. It has a very powerful computer, an NVIDIA Jetson, for neural network processing and also to perform other algorithms like path planning, control. And also we have a camera or a stereo camera plus an inertial measurement unit. The drone can actually generate accelerations up to 7 Gs, which is quite impressive if you think about. So actually it's comparable to the same first-person view drones raised by human pilots. Next slide. Now, how do we get to have autonomous drones that can perform as good or even better than human pilots? So actually, we have been working on this problem now for quite a few years. And these are 4 of the key challenges that we are currently working on. So there are many more challenges. These are the 4 that we are focusing on at my lab. First of all, we need to deal with inaccurate models of the sensors, of the actuators, of the environment, and of the physics. This will become more clear in the next slides. Another problem is to reduce latency because, as you can understand, if you want to fly faster, we need faster sensors, faster actuators, but that also implies to process these images and sensor information as fast as possible. So we also need faster algorithms. Now, when you fly fast, when you navigate fast, of course, you're going to crash a lot of robots because there is no success without failure. So how to prevent on that, especially because crashing can be dangerous for the researchers working with the drones, but also it's very costly. And also it's very tedious. So we are taking advantage more and more of simulation. Simulation is cheap, it's fast, it is safe. But as you know, it's very far from the real robot and from the real environment. So this is called the simulation to reality gap. So yes, we are building better simulators, but we are also trying to get around the problems of the simulation to reality gap. And I will tell you how. Then another point that we are also focusing on is dynamic environments, how to have robots that can navigate in actually crowded places. Next slide. So this is the traditional drone or robot control architecture. It's been successful. So it's in fact used in many commercial drone products, from the DJI drones to the Skydio drones, and even to the small NASA Mars Ingenuity helicopter that is on Mars nowadays. So how do you control a drone? Typically, you have one or more cameras plus an IMU that provide images and initial measurements. Then you have possibly a reference trajectory if the task is to actually go from A to B through multiple waypoints. Then there are three modules: state estimation, also called the visual inertial odometry module, planning, and control. Now, there is no problem typically with this architecture because it has been successful so far, but actually we have identified that it has some bottlenecks. So first of all, if you want to fly especially fast, you need to have very accurate models of your environment, of the actuators, and of the sensors, and of the aerodynamic effects if you really want to outperform humans. It turns out that the current architecture has some problems because each of these modules is actually designed individually rather than co-designed altogether, which means also that errors propagate from one module to the next module, and at the end you are going to have compound errors. Another problems are latencies that also accumulate over time through all the different modules. Next slide. So what we are actually investigating nowadays in my lab is whether we can replace either individual components of those modules with a learned component or a residual network that actually adds what is missing, what cannot be modeled, or alternative, which is what you see in this slide, which is the extreme approach to basically learn the whole model end to end. And so replace all these modules with a single learned model. That's the extreme. Okay, we didn't get there, but we are going step by step. And actually what we are doing in my lab is that for specific tasks, we are actually using three different approaches, either the full model-based approach or the one where actually we replace modules with neural networks or residual components with a network, or the end-to-end one. Next slide. Let's start with some concrete tasks. So let's have some fun now. So this is one of the tasks that we are currently working on. I find it very exciting. It's called autonomous drone racing. In this task, the goal is to actually have the drone fly through a sequence of gates in the least possible time. So that means by minimizing the time from the start to the finish. This problem is known as a time optimal flight. How do you solve it? Typically, you would solve it by generating a trajectory that minimizes the time from the start to the end by passing through multiple waypoints. However, the problem with this is that you can generate this trajectory, supposedly, after a few hours by solving an optimization problem. But the problem is that there is no guarantee that you are going to track, so to execute this trajectory, because this trajectory is going to minimize the time only if you're able to fly this trajectory with millimeter accuracy. This means that any deviation from this trajectory will lead the drone to underperform. So we have actually set for my lab a very ambitious goal. One day we would like to beat the best human pilot in a drone racing competition. But it turns out that we are still underperforming with respect to a human, even if we use the Vicon motion capture system. Why? The reason has to do with the models. The models that we are using in simulation to generate this trajectory are actually not perfect. So we are now testing and investigating reinforcement learning approaches or adaptive control approaches that are able to actually let the robot to self-improve on the way. Next slide. This is another task that we are also currently working on, which is trying to make drones fly more agilely than they are today. And here we took a very extreme task, which is autonomous drone acrobatics. So we wanted to see whether we can train a drone to perform acrobatic maneuvers, at least as good as a human pilot. And we are. What you see in this video is the first demonstration of an autonomous drone that uses an onboard camera, an inertial measurement unit, and an onboard computer to actually perform acrobatic maneuvers without relying on external motion capture systems or GPS. Now, for this specific task, interestingly, we used only an end-to-end neural network that maps end-to-end images, inertial sensors, to control commands. So for this task, we were able to do it using just a learned end-to-end control policy. Now the question is, how do you train such a control policy? Because you understand, if you want to really replace everything with a network, you're going to need a huge amount of data. Next slide. That's where simulation comes handy here. So in simulation, we can generate hundreds or even thousands of different trajectories and simulate hundreds or even thousands of robots in the real time, at the same time. And that's exactly what you see in this video. We're simulating hundreds of drones that learned in just 5 hours how to perform acrobatic maneuvers. And then what we did is that we showed that the algorithms actually were able to transfer to the real world without any fine-tuning. How is this possible? How do you make an algorithm that is trained in simulation to generalize to the real world without any fine-tuning? Well, here there are different techniques that we are investigating. One is certainly domain randomization, where you randomize all the features that you want your control policy or perception algorithm to be invariant to. Can be features in the environment, can be the mass of the vehicle, the frame, the size of the vehicle. And also what we are doing more and more now is that we are also trying to learn aerodynamic effects that are actually predominant, especially at very high speeds, like more than 30 kilometers per hour. Next slide. But still, this is not enough. If you want to make drones navigate very agilely, especially, better than humans at some point, you need to sooner or later address one of the key limitations of sensors at the moment, which is sensors are slow, but also the perception pipeline is slow. Because people working on vision-based robotics so far have been using standard frame-based cameras. Now, when you use a standard camera, you have latencies that come from different sources. The first source of the latency is the exposure time. You need to expose the image from as little as 1 millisecond to even up to 100 milliseconds in low light environment. And in addition to that, you also need to let the algorithms process the last images. That is going to take another 10 to 20 milliseconds, but that is not enough. Often you need to compute the second order dynamics. So you're going to need to compute, velocity, accelerations, and so more. So you need actually more than just a single pair of frames. Maybe you need to wait for the next pair of frames from the stereo camera. So that adds additional latency. So the question now that we want to answer in robotics is, can we create low latency and low perception processing pipelines? Next slide. We can do this by using novel sensors. For example, an event camera, but there are also novel sensors like SCAMP cameras. These are sensors that actually process the visual information differently. For example, event camera measures only the motion happening in the scene at the pixel level. And this information is streamed at microsecond time latency. Next slide. Using an event camera, we showed that we were able to have a quadrotor avoid objects thrown at it. So what you see in this video is a drone that, for example, learns to dodge objects that appear in the field of view. Using an event camera, we were able to do this with just 3.5 millisecond latency, because we didn't have to expose the frame, neither we needed to wait for the next frame to arrive. So we had actually managed to cut the processing time by at least a factor of 10. And in fact, this work that was published in Science Robotics last year, we showed that we were able to fly with relative speeds up to 10 meters per second. Next slide. And with this, I would like to thank you for your attention, and especially my group, without which I wouldn't be here today. Thanks.